Chapter 2, Influence Line Diagrams. First question you see, what are the uses of influence lines? To study the effect of moving loads on the structure, correct? To calculate the value of stress function with the critical load condition. Value of the stress function with the critical load condition. So that is also correct. We can calculate the stress function means reaction, shear force, bending moment. These are all stress functions because they are related to forces. Then to find the position of live load for a maximum value of a particular stress function. When loads are moving, for a particular position of the live load, you can get maximum value of the reaction or shear force or bending moment. D, towards all the above purposes. So all the above purposes we can use the influence lines. So first question is D. D is the answer. Then second one, what is the ordinate of ILD at B for reaction at D shown in figure below? See here, this is the question. We have a simply statically determinate beam it is. Okay. This point let us say A, B, C, D. What is this is 2 meters, 2 meters, 4 meters. Ordinate of influence line at B for reaction at D. Reaction at D means remove the support, lift it by 1. Without removing the support reactions at E and C, lift it by 1 here. The deflected shape of the beam will give you the ILD for VD. So there is a floating hinge here. When I lift it, BCD is a single one. So it will go something like this. This is ILD for VD. This is 4 meters. For 4 meters, 1, 2 meters, how much? This is asking 0.5. So ILD, this one is 0.5. So second question, A is the answer. Next, third one. A simply supported beam shown in figure 1 and 2. Influence line for the beam is drawn. Which one of the following statements is correctly associated with the figure 2? So this third question I'll write here. This is your influence line beam ABC. A, B, C. Okay, this length is L, this length is X. Now we have drawn some ILD. One you have drawn means it goes down like this, up. So this is 1. Plus he has put 1. For a distance of L it is 1. For a distance of X, X by L, naturally it is minus. This is figure 1, figure 2. Okay, LX. So this is how he has drawn. This is related to what? Influence line for shear force at B, wrong. How we got this one? To obtain this ILD, remove the support, lift it by 1 or pull it by 1. So this is ILD for VA, vertical reaction at A. Vertical reaction at A is also shear force at A. What is shear force at A? VA only. Stand here, look left. What is the shear force? VA. So ILD for VA or maximum shear or end shear we also can call it, or end shear at A or shear at A. All mean the same. This is influence line for shear at B. A is wrong. This is ILD for bending moment at B, wrong. ILD for vertical reaction at A, correct. Reaction at B, wrong. So this is ILD for VA. So C is the answer. Next, fourth question. Which one of the following statements is correct? ILD for bending moment at a section in a cantilever. This is for a cantilever at a section in a cantilever beam is a triangle extending between the section and, you see here, if I want to draw ILD for bending moment here, what you will do? Assume an imaginary hinge and rotate by 1. Theta is equal to 1. Some x distance, let us say, then it will be x theta. Like that. This is the point. Somewhere here B you take it, say. Now see the one is a triangle extending between the section and the fixed end with maximum ordinate under the section. So A is wrong. B, fixed end with maximum ordinate, wrong. C, unsupported end with maximum ordinate, this unsupported end with maximum ordinate at the section. Question is in a cantilever is a triangle extending between the section and the unsupported end with the maximum ordinate at the section. Unsupported end with maximum ordinate at the unsupported end with maximum ordinate at the section is wrong. At the section 0. So it is a triangle extending between the section and the unsupported end with maximum ordinate at the unsupported end. So D is the correct. So it is a triangle extending with maximum ordinate at unsupported end and at the section. Triangle is like this. Say minus, say. This is ILD for bending moment at any section B. Cantilever. This length is L minus X, say. Any in between you want to find ILD for bending moment, say. Assume a hinge and rotate. So it rotates like this. Now answer. Which one is the correct one? Next, fifth one. So D is the correct option in this case. Muller-Breslau's principle is applicable to get influence line for which one of the following? Reaction at the ends of simple beam, correct. Bending moment at a section, correct. Shear force at a section, correct. Forces and moments at any section, also correct. Then which one is more correct? You can find reaction, bending moment, shear force. More correct is forces and moments, because force means you can include shear force. So not just bending moment, not just shear force, it is applicable to find forces and also moments. So more correct is D. Then sixth question. What is the variation of influence line for stress function for statically determinate structure? Influence line for stress function means reaction, shear force, bending moment for determinate structures is parabolic, bilinear, linear, uniformly rectangular. It is a linear structure, determinate structures means. So 6 is, we can say linear, we can make it. 6 is C. Statically determinate structure when you are taking means it is like a cantilever beam or simply supported beam, or that's all. Cantilever, simply supported beams, it will be like a linear function only. Single straight line only will go. Okay. Next, he means that way. 6 is over. Next, seventh one. 6 is C, 7. An influence line for a function. See here he has given directly. Function means shear force, reaction, deflection. Deflection also is a function. Okay. In a structure is a curve which shows its variation at a particular section of the structure for various positions of a moving unit load. Is correct statement. Influence line for a function in a structure is a curve which shows its variation, function variation, at a particular section for various positions of the moving load. As the load is moving from one position to other position, how at a section stress function varies. That only ILD gives. So first one is correct. Second one, ILD for bending moment or shear force must not be confused with bending moment diagram and shear force diagram for the structure. Correct. You should not be confused with the bending moment diagram and shear force. Why? ILD for bending moment at any section means what? As the load is moving, how that load influences bending moment at a particular section is the ILD. Then what's a bending moment diagram? Now load is constant at different sections. What is the bending moment because of that load? Load is fixed in position, section is different. That is bending moment diagram. ILD means load is moving, section is fixed. So that much difference is there between ILD and BMD. So must not be confused. Second one is correct, first one is correct. Third one, bending moment diagram and shear force diagram show the moment or shear values at all sections of the structure. Correct. The influence line diagram for bending moment or shear force is always drawn for a moving point load and for a particular section only. Correct. Same thing whatever explained earlier. So three statements are correct. So 1, 2, 3. Which of the statements are correct is seventh question is A. He is asking you in this case what is ILD, what is BMD and what's the difference. ILD means section is fixed, load is moving. Bending moment diagram means load is fixed, different sections you have to take. Okay, seventh is that. Next, eighth question. ILD for reaction at B. There is one beam like this. Here there is a roller. There is a hinge. There is a roller. There is a hinge. There is a roller. Little overhang was there. Now what is the ILD? ILD for at B. This point let us say A, B, C, D, E, F. A, B, this he has taken E, A, B, C, F, D. Something like that. Some overhang also was there. Okay. Now without removing the supports, A, C, D, lift it. When I lift it by 1, A, B, E is one line. So it will go up to here. This I should not remove. So it will come down like this. Then it will go up like this. Then ordinates here. This is one. Now see which diagram matches this one? D. Remove it, lift it. This is the deflected shape of the beam and D will match the deflected shape. So eighth question, D is the answer. Next, ninth. ABC. This I have solved in the class. Consider the beam ABCD and the ILD shown below. ILD belongs to reaction at A, shear force at B, shear force at left of C, shear force at right of C. At the internal hinge, ordinate is 1. So you have to cut the beam at B and lift it. Since cutting is involved, it is the shear force at B. So ninth question, shear force at B. This we have solved in the class. Okay, 10th one. When a single point load W travels over a simply supported beam, what is the shape of the graph for maximum positive or maximum negative shear force? Maximum positive or negative shear force. This is a simply supported beam. When a single point load is moving, what is the graph of maximum positive shear force or negative shear force? Where will it happen? Stand here, look left, section left side upward, positive shear force, section right side upward, negative shear force. That means he is in other words, maximum positive shear force or maximum negative shear force means he is asking you to draw ILD for the reaction. Now it is a triangle with maximum ordinate W at the center, 0 at simple supports. See what is the shear force, you will get it. If I plot it, remove the support, lift it. This is the triangle. If load W is moving, let us say ordinate is W. Now let us first one, triangle with maximum ordinate W at center, wrong. Triangle with maximum ordinate W at support, correct. A rectangle with ordinate W, wrong. Parabola, wrong. So triangle with maximum ordinate W at support is correct. Any support A or B, that's the maximum shear force. Sir, in strength of material, sir might have told you maximum shear develops at the supports, which is also called end shear, because shear developed at the end of the beam. End shear, support reaction, both mean the same. Okay, next, 11th question. Absolute maximum bending moment under any given load, given wheel in a beam due to several point loads occurs when this wheel and center of gravity of the load system are at equidistance from the ends of the beam. Wrong. The wheel and the maximum load wheels, this wheel and the maximum load wheels are equidistant from ends of beam. Wrong. B, let us see. This wheel and CG of the total load system are equidistant from the ends of the beam. Wrong it is. This wheel is at midspan. What is the correct answer is the wheel and the resultant must be equidistant from the center. So that option is not there. So 11th is D. None. Load and the resultant of load system should be equidistant from center. Then you will get absolute maximum bending moment under the wheel load. Okay. Next, 12. For the fixed beam shown in figure below, ILD for bending moment at the midspan. This I solved in the class. ILD for bending moment at the midspan. Assume a hinge, he has pulled it down. So this deflected shape will be something like this. This is now positive we have to write. Okay, no problem. This is L by 8. What I have shown in the class is upward we have taken because positive bending moment above reference line. Now it is below reference line they have shown. This he has taken 12th question A. This is ILD for bending moment at center. Next 13th question. For the beam shown in figure 1, ILD is shown in figure 2. This refers to, you see here whatever section they have given there is a cut. Since cutting is involved, it is the shear force at XX, shear force at section XX. So 13th question is D. Next, 14th. ILD for support moment at A of the fixed beam AB constant EI. Fixed beam constant EI means this is the fixed beam. Any support moment, let us say. What we have to do, assume an imaginary hinge and rotate. The deflected shape will go something like this. And this theta A is 1 minus. This is ILD. Which one will match? Zero slope should be there. Here. So CD ruled out. B ruled out because there they have shown here theta B is 0 because fixed support. So correct option is A. 14th question is A. Okay, that matches the deflection profile. Next, 15th question. 15th one. ILD for vertical reaction at A. This is the problem. A, B, C. Now, what is ILD for vertical reaction at A? Without removing the supports at B and C, without removing the fixed end moment, lift it by 1. Then the deflected shape of the beam. Here 90 degrees must be there. Then when you are maintaining 90 degrees, it will go down like this. Then it will have to go up like this. So this, which one will match? A. Here 90 degrees must be maintained because fixity you didn't remove. So 15th question, A is the answer. Okay, ordinate is 1. Without removing the supports, without removing the fixed end moment, hold it, lift it by 1. The deflected shape of the beam is ILD for VA. So many problems we have done. This is one such problem. Then 16. The spans to be loaded, this I told you in the class, maximum positive reaction at P as shown in figure, or when you lift it up, PQRS. So 16th D. This is solved in the class. 17. Next, ILD for redundant structures can be obtained by Muller-Breslau's principle. 17B. Muller-Breslau's principle, you can get the ILD for redundant structures. What redundant structures we have taken? Propped cantilever, fixed beam, continuous beams, all ILDs we have drawn. Okay. So Muller-Breslau's principle states that remove the support and give unit deflection. The deflected shape gives you the ILD. Next, 18. Which one of the following equations represents IL influence line of fixed end moment B of the fixed beam AB of length L with origin at A? This is the fixed beam. Equation represents ILD of the fixed end moment at B. So this MB we want to get it. Fixed end moment at B. AB of length L with origin at A means unit load you have taken here. This is a W. This is X. This is L minus X. Okay. What is the fixed end moment? W A square B A square B by L square. Right. Here means this is MA means what? W AB square by L square. That is the formula. W A means X, B means L minus X whole square by L square. This ILD we have drawn in the class. Now he is asking this one. W A square B by L square. Now W becomes 1. 1 into X square into L minus X by L square. So X square into L minus X by L square. So 18th A is the option. If this one is for B, X into L minus X square means this is for MA. This is for MB. ILD ordinate for MB, ILD ordinate for MA. This we have drawn in the class. Now they asked for MB. Next, 19th question. Okay, 19th question. Truss panel dimensions 3 by 4 meters shown below. ILD for force in the member U2 L3. Now spans are 1, 2, 3, 4, 5, 6 spans. It's like this 1, 2, 3, 4, 5, 6. And this is height is 4 meters. This is 3 meters. Okay. This is the problem. All are connected like this. This is a hinge support. This is a roller support. This U2 he has taken. This is L3. U2 L3. Height is 4 meters. Now there are 1, 2, 3. So 6 panels at 3 meters. So you will get around 18 meters. Now truss dimensions are also given. ILD for force in the member U2 L3. U2 L3 we wanted ILD. So cut it by 1 1. Keep the load here. Now look right side. This is VB. Okay. Now this is upward means this is downward. F you call it. Okay. This is theta. What is theta? 4 by 3. Sin theta is equal to 4 by 3. 3 by 4 means 36.87. Now 4 by 3 means you will get theta is equal to 56.31. 56.1. So some value we'll see. Without that, let us see we can manage. Sin theta is 4 by 5. Okay. So directly 0.8. So calculators are not permitted. So we can manage like this. Now you see load is here. Look right side. F sin theta. I told you only this equation must be there. F sin theta must be VB. VB is 1. Sin theta is 4 by 5. 0.8. So F is equal to 1 by 0.8 means 1.25. So 1.25 ordinate. Compression. So below reference line. This is 1.25. So up to here we have to take it. For 6 panels, 1.25. 2 panels how much? 2 by 6 into 1.25. So 2 threes, 0.4. Approximately we can take it as a 2.42, or he has given. So compression 0.42 up to here. Compression, this ordinate is 0.42. So compression 0.42. Option A matches. Compression 3.3 gone. Tension 0.5 gone. Tension 0.33 gone. Enough. In 2 minutes time this is sufficient for us. Entire diagram not required. So 19th question, A is the option. Entire ILD we don't have to draw and waste the time, because we know how to draw, but we don't want to draw in the exam. He is asking what is the ordinate. Simply ILD they asked. Up to here you have drawn and only one option matches with that, 0.42 and C. So put it. That's all. Why C? Arrow mark is towards the joint. So compression. Okay, like that. Next 20. ILD shown is for the member. This also 1, 2, 3, 4, 5, 6 panels are given. 6 panels are given. Okay. Now these two are in this direction. These two are in this direction. PQRS. PQRS. Like this he has given. ILD also he has given. ILD is compression downward he has kept it. Here maximum ordinate he has given. Ordinate, and here it went up. So disturbed panel, it went like this. Say something this way. This is compression minus tension plus. Which member you have done? Disturbed panel is this one. That means out of those members only it should be there. It cannot be for RS, because RS is a pure tension member. So this is ruled out. PQ ruled out. Disturbed panel means only PS is diagonal member. So because in this panel only this disturbance is there. Okay. So this disturbed one last we will connect. That means this is ILD for PS. ILD for PS. This is for pure tension member, pure compression member. These two are gone. Next, what is left out? This one. Because in this panel only this disturbance is there. The disturbed panel we connect last. So this we connected last. Okay. ILD for PS. Now let us see what he has given A. 20th is A. This discussion you must understand. I am thinking that you have already studied the class notes. Whatever I talked in the ILDs, that you must recollect. Otherwise, read the ILD chapter fresh, then see the solutions. Next, 21. How logically we have come out to that conclusion, we have to see. Next one, 21st question. ILD for a truss member is shown in the figure. Like this, they are given the diagram. Say something like this. Negative 10 units, compression, positive 20 units. That means this is the tension area, compression area. Positive values indicate tension. Dead load of the truss is 20 kilonewtons per meter. When dead load is there, it should be kept in full. Kilonewtons per meter, this is dead load. And live load is 10 kilonewtons per meter. Live load is longer than the span. Maximum tensile force. So live load you must keep here only. This is 10 kilonewtons per meter. Live load. Longer than the span means the other span, the other load, live load will go this side. Or if it is going this side, coming from this side, say, ask the engine driver to move the out of the bridge till the tail comes and stops here. Dead load you have no choice. It has to be in full length. Whether we like it or not, dead load will remain there. Only live load you can adjust. So, maximum tensile force in the member. This is dead load plus live load. If I take this one, dead load plus live load, 20 plus 10 into positive area, 20 units. This is DL plus live load. This is positive area. Plus dead load is 20 into negative area minus 10. This is dead load, negative area. This you have to keep it. So 20 plus 10, 30, 30 into 2, 600 minus 200. So you will get 400 kilonewton. So correct option is B. Like that. Okay. 22nd question. For the pin jointed plane truss shown in figure, which of the following diagrams represents the influence line for bar in the force DI? DI is the vertical member. Okay. So some truss they have given. I'll show you how we have to resolve the issue in no time. Then there are 6 panels here also. 1, 2, 3, 4, 5, 6. One, like this was given. This is this way, this way. Okay. Whatever dimensions they have given, we wanted this this is D, this is I. I'll cut it like this. ILD for DI, if you want, how you can cut it? How to cut DI? I cannot cut this way. 1, 2, 3, 4, 5 are cut. So not possible. I must cut this way only. 1, 1. So disturbed panel is this third one. So disturbed panel is IJ. This point we take say J. Disturbed panel is IJ. So there only it should change its sign because one is compression, one is tension. So disturbed panel it changes from compression to tension or tension to compression, whatever it is. Now you see B, C, D they have given vertical lines, so ruled out. So it must gradually change. So correct option is A. You don't have to see that quickly, you have to manage. First cut it, disturbed panel, here it should change linearly, either compression to tension or tension to compression. Sudden drop in the ILD cannot happen in the panel. So correct option is A. Those ordinates you don't have to worry, because first you have to select which one is ILD. All others simply vertical lines they have given. Instead of giving a sloped line, all vertical lines they have given, which is impossible to get. Next, 23. Which one of the following diagrams represents The ILD for force in the member DG. This I solved in the class. DG member, when they ask, load is moving at the bottom line, bottom chord members. So DG member, when load is exactly at the G unit. So F and H 0, 0, G it should be 1. That means this one is 23rd question D. This solved in the class. Next 24. For the simply supported beam AB shown above, which one of the following is correct for the maximum shear at the center of span for a live load longer than the span? This is the beam. Okay. This center point is C. This is D. This is E. All L by 4, L by 4 like that. Simply say as shown in figure, which one of the following is correct for maximum shear at center of the span? If you draw maximum center of the span ILD, cut here, push it down like this. Lift it up like this. Minus plus. Center of the span means A by L is 0.5, B by L is 0.5. This is ILD for shear force at C. Now this ILD will tell you how it should be loaded. The entire span should be loaded. Wrong. Half span AC. Half span AC be loaded. Correct. AC, if you load it, keep the load here. You will get load into maximum negative area you will get. You will get maximum negative shear force at C. That is correct. The middle half of DA should be loaded. If you load here, positive area, negative area cancels out. Net becomes 0. So that is wrong. Quarter span AD should be loaded. That is also wrong. Full from here to here it should be loaded. Then you will get maximum negative shear force. So the half span AC should be loaded is correct. So B is the correct answer. 24th question B. So this ILD will tell you how you have to keep the load to get the maximum quantity. Okay. Next 25th. ILD for bending moment at section XX at a distance 4 meters from the left support of a simply supported girder is shown below. A UDL of intensity 2 tons per meter longer than the span crosses the girder from left to right. Maximum bending moment at section XX is equal to. Longer than the span it is moving. See here. This we know how to manage. A, B. Okay. Some section XX. XX. This distance is A value 4 meters, B value 12 meters. What is the ILD for bending moment at C at XX? AB by L. Like this. ILD for bending moment at C. This point let us say C. Okay. How to load it? This ILD tells you that it should be loaded full. Intensity of UDL is 2 tons per meter. And it is longer than the span. Whatever extra is there, put it outside. So this is AB by L. A is 4, B is 12, L is 16. 4 fours, 3. So you get 3. So intensity is 2. Max BM. Maximum bending moment at C is intensity of load is 2 ton per meter. Area half. Base is 16. Height is 3. So 16 into 3, 48. The values will be given such that it will be cancelled. So 25C. 26. The maximum bending moment at left quarter point of a simple beam due to crossing of UDL of length longer than the span. UDL of length shorter than the span in the direction from left to right would occur after the load had just crossed the section by. This is the question. This is the beam. This I solved in the class. AB, this is C. Left quarter, L by 4. This is 3L by 4. He is asking how much UDL should cross. This is L1 by 4, 3L1 by 4. 3/4 of UDL should cross because this C must cut the loaded span and the load in the same ratio. So 3/4 of UDL, 3/4 of its length. So 26C. This we solved in the class. Next 27. The given figure shows a beam influence line for shear force and bending moment at section 1-1. Somewhere here 3 meters, 9 meters. ILD for shear force they have drawn. Cut down, lift it up like this. This is 0.25, 0.75. Then bending moment. This we know they have already drawn 2.25. This is for bending moment, this is for shear force. The values of shear force and bending moment at a section 1, this is 1, due to a concentrated load 20 kilonewton placed at midspan. That means this point, let us say A, B, C. Load is here, whose magnitude is 20 kilonewton. Total is 9 meters, so this is 6 meters. For 9 meters, 0.75, 6 meters, 0.5, 3 meters, 0.25, 0.5, 9, 0.5. So you will get that ordinate is 0.5, 20 into 0.5. So shear force at C is equal to 10. Shear force at 1, 1. This is 9 meters, 1 meter. Center we wanted 20 kilonewton. So shear force you will get it as 10 kilonewton. So only one option is matching. Then directly put bending moment. This is 2.25. This is how much? For 9 meters, 2.25. 6 meters, how much? So 6 by 9 into 2.25. So this is 6 by 9, 2.25. Then bending moment at 1, 1. 20 into 6 by 9 into 2.25. So 3 2s, 3 3s, 0.75. So 40 into 0.75 means 3 by 4. So you will get 10 into 3, 30. So 30, 10. 10 and 30 means 27. D is the option. Next. Common data questions. A beam PQRS is 18 meters long, simply supported at points QR 10 meters apart. Overhangs are given. Train of loads. This I have solved in the class 28. Maximum sagging bending moment, you got it as 400. This is solved in the class. Then 29. Also we solved during the passage of loads 300 and minus 30. A. 30th. Hogging bending moment, you got it as 150 into 5, 750. That means D. This also is solved in the class. Next 31. A UDL of length 8 meters crosses a simply supported girder of span 20 meters. Maximum bending moment at left quarter span. This is the beam. UDL of length 8 meters. Simply supported span 20 meters. Okay, maximum bending moment at the left quarter means this is the point. A, B, C. Left quarter means L by 4. 20 by 4 means 5 meters. This is 15 meters. So left quarter means L by 4. Okay. At the left quarter span occurs when the distance between the point of CG of total load and the midspan is. Now how we have to keep the load here like this. This point is C. Okay. Now how much should cross this one? This length is 8 meters. 8 meters. That means this value 8 by 4 means 2 meters. Other length 6 meters. Okay. Now he is asking quarter point occurs when the distance between the point of CG of the total load and midspan. Where is the midspan? 20 meters means midspan is somewhere here, say. So midspan is here. D is the midspan. Total is 20 meters. This you take say 10 meters. The other distance is also 10 meters. Okay. Now from here to here 5 meters. And this is 6 plus 2 8 meters means 4 meters. This is the CG of the load. This is 2 meters means from here, from C, how much distance it is? Another 2 meters. Okay. Now he is asking from CG to D. Now from CG to this one, what is the distance you see? Here to here 5 meters. This is another 7 meters. This you have 7 meters. CG is 10 meters. So from here to here now how much is left out? 3 meters. So correct answer is 3 meters. This is simply finding the distances, that's all. So you will get 31 3 meters. Next 32. I think we understood this one. UDL is given. It should cross 3/4 of that. 6 meters it should cross 2 meters here. Now CG of the UDL means already 2 meters are over. Another 2 meters UDL will be there. So CG here. Then the other length is 4 meters. So total 8 meters. Now CG distance from here how much? Already this section is at a distance of 5 meters. Then crossed another 2 meters, 7 meters. Left out is 3 meters. Like that. That means the UDL might have gone up to here. It might have crossed that also. Otherwise 6 meters won't be there up to here. 6 plus 2, 8 plus 3, 11. So this UDL ends at 11 meters. CG is here, midspan is here, CG is here. Okay, that was simple thing. Distances measuring, that's all. 32. Maximum bending moment caused by a set of concentrated moving loads is Always at midspan, wrong. Between midpoint and concentrated load, next to the midpoint of the span, not definable. Always under a load close to the centroid of the set of loads. This is the question. The maximum bend moment caused by a set of concentrated moving loads. Some loading were there like this, say. Okay. Suppose CG is somewhere here, resultant is acting like this. CG of the load system, W1, W2, W3, 4, 5, 6. Maximum bend moment occurs if the resultant is nearer to this load or this load, say. If it is nearer to this load and resultant should be at equal distance from center. If this R is nearer to this load, then this and this should be equidistance from center. It is nearer to this load means this load must be more, so only it might have shifted. Let us assume that way. Always at midspan, wrong. Between the midpoint and concentrated load, next to the midpoint of span. That is also not correct. Always under a load close to the centroid of the set of loads. Always under the load close to the centroid of set of loads. Supposing that this is closer, W3 is closer. Suppose. Then how you have kept this point, let us say AB, this is the center C. Then you should keep W3 here, resultant here. Then all other loads you will keep it. So you see this one. Always under a load close to the centroid means this is the centroid of the load system, close to the centroid of the set of loads. It's like that. B point, why you can eliminate is between the midpoint C and concentrated load next to the midpoint of span. Between the midspan and load, somewhere in between, it will not happen. It will happen under a load, not in between. That's how you have to remove B. Between the midpoint and concentrated load, in between will never happen maximum bend moment. Always maximum bend moment happens under the point load. Then which point load? Whichever closer to the resultant, that load you will get maximum bend moment. Then how to keep that? Load and resultant should be equal distance from the center. Then maximum bend moment occurs under the load. That point some D, not at center, not under the resultant, but under the point load. That's what I have given you. So correct option 32 is D. Next to 33 question. Two point loads 2x and x spaced 3 meters apart crosses a girder of span 9 meters. This is 9 meters. If maximum bend moment occurring on the girder is 48 kilonewton meter, what is the value of x? What should be the x? Supposing that you take 2x, x, then where is the resultant? Nearer to this one, or naturally this will be 1 meter, this is 2 meters, because resultant is 3x. So x into 3 must be equal to r into 1. That means 3x into 1. So r, this will be at a distance of 1 meter. Now this you have to keep it. This is the center point. This is 2x. This is the resultant. So this is 0.5 meter, 0.5 meter. This point say D. This point say X. Okay. So maximum bend moment happens here. So ILD for bend moment at D, if you write it, this is what you will get. 0.5 meters gone means this out of 9, 4.5 minus 4. This is 4 meters up to D. This is 6 meters. Then what's the height here? ILD ordinate. This is ILD for bending moment at D. AB by L. A means 4, B is 6 by length is, no, 4 means this is 5. Because 4.5 plus 0.5, 5 meters. So 4 into 5 by 9. So 20 by 9. Now here how much? This is 3 meters. This is 5 meters. 5 meters, 3 meters. 3 meters gone, 2 meters. So this is for 5 meters 20 by 9. Then for 2 meters how much? 2 by 5 into 20 by 9. So 5 fours. So you will get 8 by 9. Now you see maximum bend moment is how much? 2x into 20 by 9 plus x into 8 by 9 is equal to, maximum bend moment he has given it as 48 kilonewton meter. This is value is 48. Now we simplify. This is 2x. Common factor if I take x, x into 40 by 9 plus 8 by 9 is equal to 48. Common factor if I take it, x into 48 by 9 is equal to 48. So x you will get 9 kilonewton, like that. So 33, 9 kilonewton, 33B is the answer. So based on the description, this resultant is 3x. So if this is 3x, the CG will be somewhere here. CG of the load system 1 meter. Okay. So from that, this is the center point C, D, this point let us say E. So 1 meter means 0.5 left, 0.5 right. So 0.5 gone. Out of 4.5, from here to here 4.5 meters. Center point means. Okay. 0.5 gone means 4 meters. This is 4.5 plus 0.5, 5 meters. So B is 5 meters, A is 4 meters. See, nowhere we require calculator. Without calculator also we can manage. Now see the 34th question. ILD for shear force at A. ILD for shear force at A or ILD for reaction at A both mean the same. You have a overhanging portion like this. Okay, this is the beam. And here there is one more roller. There is a hinge here. Okay. Now AB, C, D. Without removing the supports at B, C. Now C is not a support resting on the ground. It is resting on the beam. Suppose if beam goes down, roller also will go down. Very finite distances. Virtual displacements means an imaginary displacement. We should not assume that if it goes down so much, it may slide and slip and fall down. That much displacements will not be there. Virtual, they are. So, without removing the support at B, support at D, okay, remove the support at A and apply unit displacement like this. So, ABC is one member, it will go like this. Now on this roller is there, okay, no problem. Roller also will come down. Then this will go up like this. This is plus. This length he has given L. This length is L by 4. For L, 1 means L by 4 means it is 1 by 4. So correct option is A. Okay. Next, 35th one. An applied moment M is moving on a simply supported beam of span L. Okay, of span L shown in figure. Absolute maximum bending moment developed in the beam. This I have solved in the class. Okay, it's moving right to left. When the moment is at the support, the bending moment is M. The bending moment diagram also I have drawn the bending moment diagram also. So when the moment at the support, this is the bending moment diagram, M at support. Okay, this is what I have given. M at center, we have drawn also bending moment clockwise means anti-clockwise. Like this diagrams I have drawn, minus plus, you will get M by 2, M by 2. M at center, right? So there I told you that the external effect of a couple remains the same wherever you replace it, but internal effect will be different. So there what I am drawing is a bending moment diagram. When the M at center, when M at support. So I told you when M is at the support, you will get absolute maximum positive bending moment. So 35th question, absolute maximum bending moment magnitude is M. So B is the option. 36 also I have given you in the class. ILD for prop reaction. This is the question. Okay. Some unit load is here. 1 at a distance of x. Total is L. So VB is a function of Fx. So moment at A if you want. ILD for at A for the given equation. So you will get moment anticlockwise moment MA, you will get it here. MA is equal to VB into L, that means f of x into L minus 1 into x. Okay, anticlockwise. So, but he has given x minus fx into L. That means he has taken our anticlockwise moment. If you take this value as negative, say anticlockwise Hawking moment, if you take minus, you will get like this: MA is equal to plus x minus f of x into L. Okay, this is Hawking bending moment. Hawking bending moment, if you taken as negative, you could have got this one. So D is the option. Sagging positive, Hawking negative, if you take it, it will come that way. But even if this is there, let us say, that option is already given. Okay. So like this you should manage. 37. Area of the ILD for reaction 3L by 8. This I have given you in the class. 38. 3 wheel loads either 26 or 24 kilonewton should be placed at the section. 38 also solved in the class. Okay. Next 39. What is the shape of ILD for maximum bending moment in respect of a simply supported beam? Actually, in a simply supported beam means, if I take a section here, I get a triangle. I take a section, I get another triangle. If I add all such points, I will get a parabola like this. So at any section maximum bending moment values you take it, draw a curve. So you get a parabola this way. So you get the parabolic. So C is the option. He is not asking ILD for bending moment at a section. Section he didn't specify. Different sections, maximum ILD you take it. Locus of all such points will look like a parabola. So 39C. Now let us see 40. A beam with cantilever end shown in figure represents ILD for shear force at the section just to the right of support A. This also we have solved in the class. 40A. Solved in class. Then 41. Which one of the following diagrams correspond to ILD for moment at A? This is what they have given. Two hinges are there. Here there is a support. This point, let us say A, D, E, B, C. Okay, how do you find that? Without removing the supports at B and C, assume an imaginary hinge and apply unit rotation. When I apply unit rotation, it will come down like this. Theta A is equal to 1. This length he has given L, say. So L into 1 means this will ordinate will become L. Now you see, without removing the support here and here, it cannot be lifted up and down. So it can go up to here only. Okay, minus. That's all. It cannot go up and down because of the support here and here. This EBC beam, you are holding two locations, so it cannot be lifted when I rotate here. So correct option is A. This is ILD for bending moment or moment at A. Then 42. Muller principle for obtaining influence lines is applicable to statically determinate beams and frames. You can apply statically indeterminate structures, the material of which is elastic, which follows Hooke's law. Only that any statically indeterminate structure, it will not, you cannot apply. Any statically indeterminate structure means if you have a non-linear elastic structure, you cannot apply Muller's principle. It is applicable to linear elastic structures for which principle of superposition, that means Hooke's law, is applicable. That means within the proportionality limit only loads you have to apply. For large deformations also you cannot apply this principle. Okay, 1 and 2 are correct. 42A. Any indeterminate structure you cannot apply. Any indeterminate means it can be any non-linearly elastic structure. The Muller's principle is based on the Betti's reciprocal work theorem. Reciprocal work theorem is applicable to linear elastic structures for which Hooke's law is applicable. So accordingly, Muller also same. Okay. 43. Maximum bending moment. Maximum bending moment at a given section in which train of wheel loads move occurs when average load on the left side is equal to right side. That 43, only one is correct. One only. Because if you say more than average load on the right segment, say, when the loads are moving from right to left, let us assume, or left to right, when the loads are moving one by one, at one stage average load on AC will be less than the average load on the right side. So bending moment will happen. One more load goes, say, then also more only will come. One more load goes, then also more. You don't get maximum. Wherever change of sign happens, then it will be there. It will happen. So when all loads are on the left span, right span load is 0. Average load is 0. So it is greater. So whenever greater, you will not get maximum bending moment. One by one should cross. That greater sign should become equal or less than symbol. Any change of sign. I told you that. So it should be equal. Otherwise less than. If equal cannot happen, less than. But not everywhere, wherever less than is there. If he says more than average load on the right segment means for any value more than means it's not correct. For any load less than average load on the right hand side also not applicable. Only first change of sign only applicable. That means for all values of less than symbol, you don't get maximum bending moment. So one only is the correct answer. It should be equal. If that is not possible, then only first less than. Next less than, it won't be applicable. Okay. A beam PQRS as shown in figure subjected to moving distributed vertical load. Fourth question we have answered, solved in the class. 45th question. Muller principle enables determination of influence lines experimentally as well. Supposing that you have a beam, say, to find experimentally means prototypes, we build it and give unit displacement. Then how the beam deflects or how the structure deforms. In the same way, your influence line diagram also, wherever a deflection is more, the influence is also more. So you can find Muller-Bresla's principle enables the determination of influence lines experimentally as well. We can find experimentally also. Influence line of deflection, not a stress function, shear force bending moment. Deflection at any point in a statically determinate beam is linear. It is not linear because deflection curve means some W is there, say. So EI into bending moment at xx at a distance of x. So bending moment at xx is minus W into x. Differentiate it. So EI d square y by dx square is equal to minus mx. That means W into x. Integrate EI into dy by dx. You will get wx square by 2 plus c1 EI into y wx cube by 6 plus c1x plus c2. So it's a cubic curve. If w becomes 1, supposing that, then for different values of x, if you plot a graph, you will get a influence line diagram. You will get a third degree curve. So ILD for deflection curve is a third degree curve. ILD for deflection is a third degree curve. Okay. So it is not linear, it is a third degree curve, which means that for the fifth question, second option is wrong. It's not linear. It is third degree curve. Second is wrong. One is correct. Third one, moment distribution, slope deflection, matrix methods can be applied to compute the ordinates of influence line diagram at the required locations. You can find, I told you, for a frame, when you want to draw ILD for MA, then you have to find a MA expression by using slope deflection or moment distribution or matrix method. Then MA value, once you get it, plot the graph. So to find the ordinates, we can use matrix methods. So 3 is correct. Influence lines cannot be drawn with the help of virtual displacements. By making use of principle of virtual work can be drawn. First of all, influence lines diagrams can be drawn from the principle of virtual work only. As I told you in the class, this is virtual displacement. Supposing that you have a beam like this, say, you give a virtual displacement of 1, okay, then W is there, plus VA into 1 minus W into Y is equal to 0. From this VA you will get, if W becomes 1, VA becomes Y. So this is how the influence line diagrams are drawn for the statically determinate beams. Remove it, give a virtual displacement, then apply principle of virtual work. So can be drawn using the principle of virtual work. That means 4 is wrong, 2 is wrong. So 1 and 3 only are correct. So 45B is the correct option. You can use matrix methods. You can find the influence ordinates by experimentally also. So the other things, ILD for deflection is not linear, and influence line diagrams can be drawn from the principle of virtual work. So that's why 2 and 4 are wrong, 1 and 3 are correct. Okay, next, 46. Now see 46th question. Balanced cantilever bridge. Which one of the following corresponds to ILD for VA? One beam is given. Two supports are there. Two internal hinges are there here. One more support. One more support. Okay, this point let us say A. That's it. Right? This is say B, C, D, E, F. He is asking ILD for VA. Without removing the supports at B, E, F, remove the support at A and apply unit displacement. Then how it will deflect? I should not lift it. It will come down. Okay, up to here. Then I should not lift this. When I am holding DEF at two locations, D cannot move up. Goes up to here. Plus, minus. So, correct option is C. 47. This we solved in the class. Only 1 and 2 are correct. 47C. 48. A Warren truss, this we will explain. A Warren truss is supported as shown in figure 1, 2, 3, 4, 5. Okay. One, 2, 3, 4, 5. This is a Warren truss supported here at L0 and L4. Okay, this is L1, L2, L3, whatever may be the numbers. U0, U1, U2, U3, U4. This is L5. This height is 4 meters. 4 into this span is 4 spans at 5 meters, 20 meters. And this is 5 meters. Now we have to draw ILD for U3, U4. ILD for U3, U4 when you draw, how you have to cut it? Reactions, let us say VA, VB. Okay. U3, U4 ILD if I want, I can cut this way or I can cut this way, our choice. Let us say I am cutting it by 1, 1. Load is anywhere between L0 to L4. Then I'll cut, look right side. See, no load here. I assume that this is a compressive force, let us say F, U3, U4. No load here because I am looking right side. These two are cut members. Cut members are meeting at L4. If I take moments of all forces about L4 is equal to 0, F U3 U4 into 4 is equal to 0. That means F U3 U4 is equal to 0. That means for all positions of the load between L0 to L4, it should be 0. Straight line, that's all. Up to here, over. Now if load is somewhere here, say, unit load, then clockwise, this is clockwise, so it has to be anti-clockwise. Then another case I can take it, second case, here itself is over actually, only one diagram was there like this. Now in the second case, I will not take it this way, I will take it like this. Because it is clockwise, this is anti-clockwise. So take moments of all force about L4 is equal to 0. The second case it is minus FU3 U4 into 4 plus this is 1 into 5. So FU3 U4 is equal to 5 by 4, 1.25. So when load is here, ordinate is 1.25 up to here 0. It is tension, right? So arrow mark is away from the joint, so tension. Plus this is 1.25. So which option matches like this? You see here 1.25. 0 plus 1.25 means D is the answer. 48, D is the option. This is valid whenever load is between anywhere between L0 L4 it is 0. Then that matches only with D. This analysis simply waste of time. Once you find this one, you stop the work, take it, go to the next problem. Then 49. A simply supported beam with overhang traversed by concentrated movement left to right. You see here, there is a simply supported beam. A concentrated moment M is equal to 1 is moving. This is moving like this. This is L by 2. This is L. M is clockwise, so reaction is anti-clockwise for all positions. This point let us say A, this point say B. So VA is equal to 1 by L, VB is also 1 by L. Constant. So downward VA is left to right. ILD for reaction at B upward. For all positions 1 by L constant. That's what I have given you. So it looks like a rectangle. Wherever unit movement is there, this is 1 by L. This is ILD for VB. For all positions of movement, reactions are same. So ILD for VB is a rectangle. So C you will get. Full rectangle from the C to B. C to B full rectangle only. Whether it is here or here or here at the support or here or here or here, same. Okay. Next, assertion and reasoning questions. 50. In a cantilever, ILD for deflection at free end. Deflection at free end. ILD for deflection at free end. When the unit load is here, we know WL cube by 3A and the ordinate must be L cube by 3A. As it goes inward, then the deflection at the free end decreases in a third degree equation we have studied. Like this it goes. Third degree curve. Okay. ILD for deflection at the free end is the same as elastic curve of the beam due to unit load placed at the free end. Now, this point A, B, let us say. Apply unit load here. The deflection is WL cube by 3A. Okay. Now, this is the deflection profile. Due to unit load, here deflection C I want to find, say. This is some Y. Okay. So, due to unit load, deflection at C is Y. Now the unit load moves, say, from Maxwell's reciprocal displacement theorem. I keep, this is C, A, C, B. I'll keep unit load here, 1. Then it will be a curve, it is a straight line. What is the value here? When I apply 1 here, deflection is Y here. When I apply 1, deflection must be Y only. Right? So, this is from Betti's reciprocal work theorem. This is the deflection curve. This is also deflection curve. Two specific cases we have taken. When unit load is here, I know what's the deflection. I found that this is the deflection curve, let us say. Some deflection here we can find from strength of materials. 5L cube by 6A, something like that you will get. That is a Y, I call it. Okay. Now, if the load comes here, then deflection here is what? Y. So, when the load is here, the deflection curve, this is the deflection curve we have drawn. So this 1 into y, if I write it, okay, 1 into y is the same as the earlier one, this 1 into y, this 1 into this deflection, 1 into y, okay. Then here this 1 into this y, 1 into y, 1 into y, both of them are same from Maxwell's reciprocal deflection theorem or Bette's reciprocal work theorem. So your assertion cantilever ILD for deflection curve at the free end is the same as the elastic curve of the beam due to unit load placed at free end. Unit load placed at free end is this one. This is also ILD also. Because when the load is kept here, load into this ordinate, I will still get deflection at the free end because of the Maxwell's reciprocal deflection theorem. So assertion is correct. Reason. See, Maxwell's reciprocal theorem, the deflection at the free end due to various positions of unit load on the span equals deflection at those places of unit moving load due to static unit load at the free end. Static unit load at the free end, if it is there, deflection at different locations means the same thing. That's what Maxwell reciprocal theorem tells you. So assertion, reason are correct. Reason is the correct explanation. So correct option is A. This is what we have studied in the Maxwell's reciprocal deflection theorem. Now I want to find this the deflection ILD for deflection curve, say. Then I keep unit load here. This is the deflection. W I am keeping. So W into L cube by 3A. Supposing that same W, if I keep it here, what is the deflection here? W into this only. W into this will give you a deflection here. So that's how you will get. That means unit load when I am keeping whatever deflection I am getting. If I keep W here, deflection at the free end will get the same. So assertion and reason are correct. Next, 51. What 51 tells is Muller-Breslas principle is a most widely used method to determine qualitative influence lines in an indeterminate structure. It will give you, as I told you, qualitatively only. Quantitatively means curve magnitude. If you want, you have to take your elastic analysis only. Okay. Next, reason. The determination of qualitative influence lines is often of great value in ascertaining the most severe stresses at specified sections in a structure. It is also correct, but not the explanation, because qualitatively influence lines, how will you determine? From the Maxwell's reciprocal deflection theorem, not because of great value it has. It comes because of the Maxwell's reciprocal deflection theorem or Bette's reciprocal work theorem, not because it is determination is of great important value. So assertion and reasoning are correct. Reason is not correct explanation for the finding the qualitative influence lines. So assertion is correct, but R is not correct explanation of A means 51. B is the option. Okay. Reason is correct, but it is not correct explanation for the assertion. That to determine qualitative influence lines means how do you determine how it came assertion from the reason of Maxwell's reciprocal displacement theorem or Bette's reciprocal work theorem. Okay. Next, 52. Influence line diagram for shear force at fixed end of a cantilever beam. This is the influence line diagram for shear force for fixed end of a cantilever beam. ILD for shear force at A. This is what I have given. Cantilever beam due to unit load, I repeat, ILD for the shear force at fixed end of a cantilever and SFD due to unit load at free end are same. Second case, if I apply unit load here, say, what is the shear force diagram? Same. This question, same. 1, 1. So ILD for shear force at A, shear force diagram are same. So assertion is correct. Then reason. ILD for bending moment at fixed end of a cantilever beam. Fixed end of a cantilever beam ILD is what? Like this. Right? Minus. This is L. This is theta is equal to 1. This is ILD for bending moment at A. And bending moment due to unit load at the free end are same. Due to unit load, bending moment diagram, how it will go? Like this. This is bending moment due to unit load. Due to unit load at B. Suppose like this you say, this is ILD, this is the ILD, this is the BMD. So they are not same. So assertion is correct, reason is false. So both A is true but R is false. So C is the correct option. This is the number 52. 51B over. Now 52 explanation is this one. ILD for shear force due to unit load SFD are same. So assertion is correct. Reason, due to unit load bending moment diagram. So ILD for bending moment at A. This is A. ILD for bending moment at A is like this. Then when unit load, if you keep it here, bending moment is this one. See, these two shapes are not same. That means reason is false. A is true, R is false. So 52, C is correct. A is true but R is false. Next 53. This 50th question, 52 question same. Apply unit load, find the deflection. Then that is what you get is the deflection curve itself is ILD because of the Muller's principle, because of the reciprocal displacement. Okay. Now let us see the 53rd question. When a single load crosses a simple span of any length, W load is there. This point, let us say A, length is L, and it is moving right side. Okay. When a single load crosses a simple span of any length, the shear force under the loads, to the right, for all spans is constant. This is a B, let us say you take it. This is VB, what is the formula? W A by L. VB is, VA is WB by L. This is the formula. So the shear force on the right side, this WA by L, wherever load is there on the right side, wherever you take it here, shear force is constant. This is what he is asking. When a single load crosses a simple span of any length, the shear force under the loads to the right, load to the right, for all spans is constant so long as the load maintains same A by L ratio. If A by L ratio is constant, shear force is also constant. Suppose load is moving like this, say A became 2A, then length also becomes 2L. As A value is increasing, length is also increasing. Length of the span is also increasing, let us assume. Then only A by L ratio constant. As long as A by L ratio constant, shear force on right hand side of the point load, you see, stand here, look right. VB is the shear force, W into A by L. If A by L ratio is constant, shear force is constant. So assertion is correct. So long as the load maintains same A by L ratio, accepted. Next reason. When the load maintains the same A by L ratio in all spans, the reaction at the right hand support remains the same. The reaction at the right hand support remains the same. This is the reason for shear force to be constant. So assertion, reason is correct, and reason is the correct explanation for the assertion. So 53 is the A. Next 54. For the two system of loads applied separately to the beam as shown in figure below, this is 54. This is again Maxwell's or Betty's reciprocal work theorem. Two system of loads. This is the load system. You just cut it. Now the 54th question also again Betty's reciprocal work theorem. For the two systems of loads applied separately to the beam as shown in figure below, two system of loads are like this. Here load is W by 2. Here also load is W by 2. Because of this, the deflection profile is like this. Okay, this is delta. Second system is like this. Okay, you apply unit load here 1, and the deflection profile is like this. Straight line or whatever it is, displacement. This is Y. This is also Y. Okay. So two systems of loads. For the two systems of loads applied separately to the beam as shown in figure below, the equation for the unknown deflection delta using reciprocal theorem is delta is equal to W into Y. Now let us first apply reciprocal work theorem. What it tells you? Load in the first system into displacement in the second system must be equal to load in the second system into displacement in the first system. So you see W by 2 into work done by, this is a P system, let us say. This is Q system. Q system of forces. Work done by P system of forces is equal to work done by Q system of forces. Q system of forces. Okay. Q system of forces work done means displacement in the P system you have to take. So W by 2 into Y plus W by 2 into Y. This load will not do any work here because displacement is 0. W by 2 into Y plus, now you see load is downward but displacement is upward. So minus I can write. So here load is downward, displacement upward. So minus W by 2 into Y. Okay. This is the system. Must be equal to work done by Q system. One is downward but deflection is downward. So deflection is upward. So minus 1 into delta. So you will get W into Y is equal to delta. This is from Betty's reciprocal work theorem. In matrix methods also I have given you about this Betty's reciprocal work theorem. Shown the equation for the unknown deflection delta using reciprocal theorem is delta is equal to W into Y. Correct. Reason: the equation for the unknown deflection delta from the influence line diagram for deflection at midspan is delta is equal to W into Y. Equation for the unknown deflection delta at midspan. So this is the ILD, let us say. If I take ILD like this ILD also looks as Q system of forces same. So equation for the unknown deflection delta from the influence line diagram for the deflection at midspan is equal to delta is equal to W into Y. W by 2 into Y, W by 2 into Y. Same. So this is from the influence line diagram also will get the same thing, because this is the influence line diagram for the deflection at midspan. So W by 2 into Y, W by 2 into Y. You will get the deflection at midspan. Okay. So assertion and reason is correct, and reason is the correct explanation for assertion. So 54, A is the correct one. What it means is influence line diagram. You have drawn one influence line diagram for the deflection at midspan. Then for unit load, if I keep it at any point, so 1 into y is the deflection at center. 1 into y is the deflection at center. If at all 1 is there. If w by 2 is there, w by 2 into y will give you not deflection here, deflection at center. Here also same thing, w by 2 into corresponding influence line coordinate will give you not deflection at the free end, deflection at center only, because this entire ILD is for deflection at center only. So load into corresponding coordinate gives you deflection at center. Okay. So this behaves now like ILD, influence line diagram. So this is assertion and reasoning are correct and explanation is also correct. Next 55. Whether it is maximum bending moment at a section or absolute maximum bending moment, the moving UDL should cover the entire span of a simple beam if span is less than loaded length. Span is less than loaded length means loaded length is more than the span. Two cases we are taking. Whether it is maximum bending moment at a section A, B, D, you take it. This distance let us say A, this distance let us say B. Influence line diagram is AB by L, right? Now to get maximum bending moment here I must cover full UDL because loaded length is more. So I will get maximum bending moment at D. Then absolute maximum bending moment you will get at center. This is ILD for bending moment at D. This is ILD for absolute maximum bending moment at center. Okay. Now if I take absolute maximum bending moment which occurs at center when UDL is there, this is what AB by L means L by 2 into L by 2 by L. So L by 4. Then UDL must be kept full length. I will get maximum bending moment. So first statement you see whether it is maximum bending moment at section D or absolute maximum bending moment at center, the moving UDL should cover the entire span of a simple beam if span is less than the loaded length. Span in length is less than the loaded length means this UDL is longer one. So much load is there, so you can put it over the full length. So assertion is correct. Reason. Whether it is maximum bending moment at a section or absolute maximum bending moment, the moving UDL should be divided by the section in the same ratio in which the section divides the span if the span is greater than loaded length. That's what is given. I told you earlier, whatever ratio the section divides the span, in the same ratio the section must divide the UDL. If at all load is shorter than the span or longer than the span, also same reason. Okay, divides the span if the span is greater than loaded length. So assertion reason is correct and reason is a correct explanation for assertion. So A is the correct answer for this. Next, numerical data type. This is for the 20 marks questions. So 56 question not required with 120 kilonewton load leading. This numerical data we can solve it, but I think here it is not required. Now 57 I will repeat because the numerical long questions I will do it in the mains when we are covering the mains. Now 56 we can calculate from our 2 marks questions. Same concept is involved here also. So no need for that. Next 57, propped cantilever is shown below. Vertical reaction at fixed end. See here, this is a 2 marks question actually. Hinge was there here, 80 kilonewton, L by 2. So if you want to find vertical reaction VA, strength of materials concept we should not use it. You should take the help of ILD. What is ILD for VA? Without removing the fixed end moment, without removing the support, remove the reaction, lift it by 1. It will go like this. Then like this. This is ILD for vertical reaction at A. Okay, plus. So VA how much? 80 into corresponding ordinate. See, 80 into this ordinate. This one, as I told you, the Betti's reciprocal work theorem or Maxwell's reciprocal displacement theorem as taught by strength of materials, sir. You must thoroughly read it. Load it in the first system, load in the second system. P system of forces, Q system of forces. P system of forces into displacements in the Q system must be equal to Q system of forces work done in the due to P displacements. So that reciprocal is valid. Those loads in the P system of forces, some places loads are there. Q system of forces, same location loads need not be there. Anywhere it can be there. Still your reciprocal work theorem is valid. So from that reciprocal work theorem, all the 4 questions they have given, so they are valid from that point of view. Here it is simple, as I have already told you in the class. Then 58. Now you see ordinate at point E of the influence line diagram for MA. So this was something like this is given. It's fixed here. This point let us say A, B, somewhere here E, F, C, D. Okay. Now this is 2 meters, 1 meter, 2 meters, 2 meters. This is 5 meters. 3, 4. This is 4, this is 3. So loads generally will not move on the inclined line, whose horizontal projection, if I write it, it will go now something like this. I am showing you the horizontal projection. 5, 4, 3 means its horizontal projection is 3 meters. A, B is here, 3 meters. E is here, 2 meters. F, 1 meter. C here, this is FC is 2 meters, 2 meters. Then ILD for question is value of ordinate at point E. At point E in influence line diagram for MA when unit load moves over the portion BD. Unit load is moving here BD, movement ILD for MA. So assume an imaginary hinge and apply unit rotation like this. Theta A is equal to 1. Load is moving from B to D somewhere here only. It goes like this. Then IL value of ordinate at point E. This is B, this is E. How much? 5 meters. So 1, this ordinate is 5 meters. Okay, value of ordinate at point E in influence line diagram for moment at A. Supposing that if load is here, say, what's moment at A means load into 5 meters. So 1 into 5 will give you moment at A. So that's it. Unit load moves over the portion BD is like this. So whenever you have inclined members, take the horizontal projection, finish off. So 59. This point we have learned already. A simply supported beam AB of span 24 meters. We solved this question already. The span is 24 meters. Two wheel load system acting at a distance d is equal to 5 meters. This is 5 meters. The wheel load P is 3 kilonewton. 3 kilonewton, 3 kilonewton. Resultant is this one, R, 6 kilonewton. Acts at a distance of 2.5 meters. That means this is the center point, let us say A, B, C. Then 3 kilonewton you have to keep it here. 2.5 means this is 1.25. This is the resultant. 1.25 meters. This is 1.25 meters. Another load is somewhere here, 3 kilonewton. You have to keep the load like this. May occupy any position along the beam. I section is given, section modulus is given. Maximum bending stress due to the wheel loads in gigapascal. Okay, C, D, E, I have to take it. So 1.224 means this is 12 meters. 12 minus 1.25, this value is A. So 12 minus 1 means 11, 10.75 meters. From here to here already 12 is there, 13.25, 13.25 meters. So if I draw ILD for bend moment at D, it will go like this. Okay. So this ordinate you will get AB by L. I'll show here. I remove this part. This I think all of you have understood. Okay. Now, if I take AB by L ordinate, A is 10.75, B is 13.25 divided by 24, AB by L. Then here you will get this value. That means 5 meters you have to remove. 13 minus 5, 8. 8.25 meters. This is 13.25 meters. Okay. Two ordinates you will find. Then maximum bending moment. What you get now is absolute maximum bending moment at D. So you will get 3 into this value we found. If you calculate when you are taking absolute bending maximum bending moment at D, I'm multiplying here AB by L, 10 into 13 by 24, you will get 5.935 meters, and linear interpolation when you take it 3.7. So 3 into this plus 3 into that. So 3 into this plus this, 28.905 kilonewton meter. And he says this problem we solved in the class also. Section modulus is given 16.2 centimeter cube. In other words, 16.2 into 10 to the power of 3 mm cube. So you will get bending stress, maximum bending stress. You will get m by z. So 28.905 into 10 to the power of 6 Newton mm by 16.2 into 10 cube mm cube. So you will get its value as, if we calculate, 28.905 into 10 to the power of 3 into 1000 divided by 16.2. You will get 1784.2 newtons per mm square. 1000 Newton per mm square is 1 GPa. So I can write it as 1.784 GPa. Gigapascal means 1000 MPa is 1 GPa. So 3 points when you remove it, 1.784 GPa you will get. Okay. So that type of questions we have solved in the regular classwork also, where I have given you PQRS overhanging beam. You calculated first absolute maximum bending moment, then section modulus. If given, you can calculate bending stress. Because it is only a 2 marks question, 2 minutes you have to complete, only simply supported beam, no overhangs. How to keep the load to get absolute maximum bending moment. Once that bending moment is known to you, M by Z you will get the bending stress. Okay, 2 minutes you have to complete this task. It was one of the year's GATE question. Okay, so this is about the influence line diagrams. Okay, now let us see the arches. Now we'll see the third chapter, arches. In that first question, a uniformly distributed load of 2 kilonewtons per meter covers left half of span of a 3-hinged parabolic arch. We have a 3-hinged parabolic arch subjected to left half means like this. Left half of the parabolic arch of span 40 meters and central rise 10 meters. Which of the following statements relating to different functions at the loaded quarter point, that means AC point, are correct? The slope is tan inverse 1 by 2. Covers left half of the span of a 300 parabolic arch you given relating to different functions at the loaded quarter point. Loaded quarter point means 1/4 of this one. This one, loaded quarter means this one. This is 10 meters, 10 meters, 20 meters. Okay. At this point, now we know VA, HA also we know, VB, HB. Slope at this point, ABC is over D, we want to find the slope. So AD you have to take it. This point, this is A, this is a D. This length is say 10 meters, X value is 10 meters. This is Y. What is Y? Slope means dy y is equal to 4h by L square into x into L minus x. Dy by dx is nothing but tan theta 4h by L square into L minus x square. XL means L, x square means 2x. So at a distance of x is equal to 10 meters, at x is equal to 10 meters, tan theta is equal to 4h is 10 meters by 40 square into 40 minus 2 into 10. So 1 by 40 into 20. That means tan theta. Theta is equal to tan inverse 1 by 2. Slope is tan inverse 1 by 2. So first statement, slope is tan inverse 1 by 2. Correct. Next, normal thrust is 6 root 5 kilonewton. At this point, normal thrust we want to find. To find the normal thrust, first we require say VA, VB. You take it as a simply supported beam. If I take it, VA is equal to total load WB by L means this load magnitude is 2 kilonewtons per meter. Covers only on the left half. Okay. So normal thrust we want to find. If you take normal thrust means this is this one, let us say. Normal thrust means this one. Normal axis you can take it. Normal axis. Radial shear also is given. Shear force is not 0. Bending moment is 0. So some questions they have asked. So this is normal thrust, shear force is in this direction. This is theta. So that tan inverse 1 by 2. Tan inverse 1 by 2 is the slope. How much is that? 26.57. Because if calculators are not permitted, we can leave it at that. So there is UDL here. Downward load how much? 10 into 2, 20 kilonewton downward. Then upward, this is 20, total 40 means the reaction here you will get VA is around 10. See WB by L. If I take it as a simply supported beam, subjected to the point load, 2 into 20, 40 kilonewton. This is now 10 meters, 30 meters. So VA you will get WB by L means 30 kilonewton. VB is 10 kilonewton. These are the reactions. VA is 30, VB is 20, 10. So 40 tallied. So VA is 30, this is 20. So there is a net force downward, there is a net force of 10 kilonewton down. Okay. So this we know theta. This is theta, this is also theta. Then horizontal thrust. Now we have seen theta is equal to tan inverse 1 by 2. This first statement was correct. Now second statement he is asking about normal thrust. Normal thrust at this point. To find normal thrust, this is over now. This part I will remove. Y slope is this much. Now when you want to find the normal thrust, you require tan inverse 1 by 2 means like this. 1, 2, this is theta, this is root 5. So cos theta you will get 2 by root 5. Keep this value like that. Now horizontal thrust means if it is full UDL is there, WL square by 8H. Half load is there, WL square by 16H. So horizontal thrust HA you will get WL square by 16H. W is 2, length is 40, WL square by 16 into height is 10. So you will get around 2 into 8, 1600 by 80. Cancels out, you will get around 20. Okay. Horizontal thrust you are getting 20 kilonewton. So when horizontal thrust is 20 kilonewton, this value is 20. Okay. No, this is up 30 up, 20 down. So this is now 10 down should be there. And this point is not 26.67, 20. Okay. Now normal thrust. This point let us say HD. HD cos theta plus this point, this 10 we can take it as a VD. VD sin theta. So to get a uniform result, divided by cos theta. Normal thrust by cos theta is equal to HD plus VD tan theta I can write. So HD horizontal this is 20 plus VD is 10 into tan theta is 1 by 2. So you will get 25 kilonewton. Now normal thrust is 25 into cos theta. What is cos theta? 25 into 2 by root 5. So you will get 50 by root 5 kilonewton. This is the normal thrust. What he has given normal thrust is 6 into root 5. Cos theta is 2 by root 5. So entry both sides we are dividing by cos theta. So root 5 and root 5 if you take it, 10 root 5 you are getting. This can be written as 10 root 5 because 50 into root 5 by into root 5. So 50 by 5 is 10 root 5. So normal thrust is wrong. So second statement is wrong. He has given 6 root 5 means we are getting 10 root 5. Then shear force is not 0. Shear force is not 0, correct. Third statement is shear force is not 0. This is correct. Bending moment is 0 is wrong. He says bending moment is 0. This statement is wrong. So what is correct is 1 only. So first question is C. What is that? Slope is tan inverse 1 by 2. Normal thrust, he gives you 6 root 5, but we got 10 root 5. Shear force is not 0. Shear force is not 0 is correct. So 3 is correct. 1 and 30, 10 down was there. So shear force will exist. Shear force is not 0 is correct only. 1, 1 is correct, 3 is correct. Shear force is not 0 is correct. One, two. Shear force, suppose radial shear when you calculate at this point, you will get how much? Radial shear radial. 20 sine theta, 20 sine theta upward minus 10 cos theta. Okay. If you take the again divided by cos theta, 20 tan theta minus 10. This is SR by cos theta. So 20 tan theta means 20 by tan theta is 1 by 2. So 20 by 2 minus 10. So shear force is 0 you are getting. So radial shear is 0. He says not 0. So 3 statement is wrong. 1 only is correct. So with this analysis, you can come to the conclusion. Slope is tan inverse 1 by 2. Then normal thrust. Normal thrust is 10 root 5. We are getting. Then radial shear. Radial shear is 0 because you are getting radial shear like this. Shear radial. Then fourth one, bending moment is 0. Bending moment is not 0 because bending moment will exist at that point. So out of this now only one is correct. So first question C is the option. C one only is the correct answer. Next. Second question, a three-hinged parabolic arch. We have a, you see in all these calculations you don't require any calculator at all. 20 tan theta means 1 by 2, so it becomes final 10 minus 10, 0. Okay. Now, the second question, a three-hinged parabolic arch having a span of 20 meters and rise 5 meters carries a point load of 10 kilonewton at quarter span. That means 5 meters. This is 15 meters at quarter span from the left end as shown in the figure. The resultant reaction at the left support and its inclination with the horizontal. So resultant reaction is asking VA, HA. So VA you can write WB by L. W is 10, B is 15, length is 20. So you will get 10 by 15 by 2 means VA is 7.5 kilonewton and VB is 2.5 kilonewton. Then HA, horizontal thrust at A. How do you find this one? Draw ILD. This height is L by 4H. A length is 20 meters by 4 into H is 5, 21. So if this is 1, here it is 0.5. So 10 into 0.5, 5. So HA will get 5 kilonewton. So HA 5, VA 7.5. Now the resultant reaction RA. So RA is equal to square root of VA square plus HA square. VA is 7.5 square plus 5 square. So you will get, so first two things are ruled out. CD is ruled out because you got 7.5. So this value must be 9.01 kilonewton. Then tan theta. Now angle of inclination with respect to horizontal, this theta. So tan theta is equal to opposite side is 7.5, adjacent side is 5. So 1.25, 1.5 by 1, that means into 2, 3 by 2. Tan theta is equal to 3 by 2. So tan inverse 3 by 2. So it will not be, if this is say 7.5, this is 5. 5 is there, let us say, then it is 45 degrees. If it is more than 5, it is more than 45 degrees. You don't have to calculate. So more than 45 degrees means 56.31 degrees. It is greater than 45 degrees. So without calculation, we should manage like this. So A is the option. See, to answer this question, because calculators are not permitted, square root of 7.5 square plus 5 square cannot be 7.5, cannot be 2.5. So C and D ruled out. So it must be 9.01. Next, is it 56 or 33? Now is the horizontal, you see. This is 5 kilonewton, this is 7.5 kilonewton, vertical reaction. 5 is there, say then tan theta is 5 by 5, 45 degrees. If it is more than that, more than 45 degrees, so 56.31 degrees, natural option is that. So that's how process of elimination. Second question, A is the answer. See, nowhere we used the calculator. Next, third statement, third question. Consider the following statements with respect to arches. The normal thrust at any section of the arch is the component of interacting forces of the section along the tangent to the center line of the arch. Tangent to the center line of the arch, whatever force you are getting, it is called normal thrust. It is correct. Radial shear at any section of the arch is the component of the interacting forces on the section along the normal to the center line of the arch. Normal to the center line means I have told you shear radial. So that is also correct. The intercept between the given arch and the linear arch at a section is proportional to the bending moment at the given section. That is also correct because Professor Reddy's theorem tells you that linear arch and the given arch, as the intercept increase, the difference increases, bending moment also increases. So that third one is from Professor Eddy's theorem. So three statements are correct. So third one, A is the option. Next, fourth one, which one of the following is associated with rib shortening in arches? Either due to change in temperature or lack of fit to cause stresses in the arch members. Rib shortening occurs in what is the question? Only two hinged arches and not three hinged arches. You see, rib shortening in arches due to temperature change, lack of fit. I told you due to temperature change or lack of fit, no stresses are developed in any part of the structure in a statically determinate structure. So due to these causes, no rib shortening will happen because no force will develop in a three-hinged arch. So only two-hinged arches and not three-hinged arches. So that statement is correct. I have given you due to lack of it, temperature change, yielding of support, sinking of supports, no forces will develop. So no question of rib shortening. Rib shortening means compression in the member. Okay. But if you apply load in a three-hinged arch, then compression will develop because horizontal thrust will develop. But due to temperature change or lack of it, no horizontal thrust, so no rib shortening. B. 2 and 3 hinged arches. So B is wrong. 2 and 3 hinged arches will not develop. Only 2 hinged arches and not 3 hinged arches is correct. C. 2 hinged arches made of reinforced concrete only. Not necessarily reinforced concrete. Even if it is made of steel, then it will cause the stresses. So C is wrong. Only 3 hinged arches. It will not so, but not 2 hinged arches. So D is also wrong. So only 2 hinged arches and not 3 hinged arches is correct. Okay. Due to temperature change, lack of fit, and also yielding of support, sinking of support, no forces in the arch. So no rib shortening will develop in the 3 hinged arches. So A is the correct one. Next, 3 semicircular symmetrical 3 hinged arches have radii 5, 7.5, 10 meters respectively. And this is what? 3 semicircular arches. If you have a semicircular arch, symmetrically 3 hinged arches. Okay. So in the horizontal thrust, you will get W by pi. So independent of the radius, horizontal thrust is same. So it is independent of the radius. 5, 7.5, 10 arch support, and each arch supports a point load W at its crown. What is the ratio of horizontal thrust in these arches? Since horizontal thrust is independent of radius of the arch in a semicircular arch, so whether it is 2.5, 5, 7.5 is the radius, thrust magnitude is same. So so you have the fifth one, C. Because if you apply load W, this is W by 2, W by 2. What is the horizontal thrust you will get? What is if you take the bending moment at C is equal to 0, let us say. This is the radius R. This is also some radius R. Bending moment at C is equal to 0. A, B, C. Okay. So bending moment at C 0 means plus W by 2 into R minus HA into R is equal to 0. So HA you will get W by 2. That's all. It is independent of R. So whether it is R is 2.5, 5, 7.5, thrust is same, W by 2, that's all. So C is the option, 1, 1, 1. Ratios are 1 and 1 and 1. Next, sixth point. For a symmetrical three-hinged arch of span 12 meters, rise 2 meters. Arch of span 12 meters, rise 2 meters. The influence line diagram for horizontal thrust at either support is to be drawn. Okay, at either support is to be drawn. Like this you will get. What is the maximum value of influence line ordinate? L by 4h. Length is 12 meters by 4 into h is 2. So 3 by 2, 1.5. So sixth question, C is the option. This ILD for horizontal thrust. We know that this L by 4h is ordinate. That's all. Simple questions they ask you. Next, seventh one. We'll write here. A symmetrical parabolic three-hinged arch of span 8 meters. Arch of span 8 meters. Central rise 4 meters. Got a concentrated load of 10 kilonewton at a location P with coordinates 2, 3. 2, 3. This is 2 meters. This is 3 meters. This point is P. And at this point, we have a load of 10 kilonewton. From left hinge. What is the bending moment at P? So, this is 2 meters. This is 6 meters. Okay, bending moment at P means analysis only is better. VA. VA is WB by L. So 10 into 6 by L means 8. So 60 by 8. Then HA. To find HA, see W L by 4H will write it. This is L by 4H. How much length is? 8 meters. L by 4 into H is 4. 8 by 16 means 0.5. So this is at a distance of 4 meters. 4 meters 0.5, 2 meters 0.25. So 10 into 0.25, 2.5. So HA you will get 2.5. VA 60 by 8. Okay. W L by 4H. Okay. Now HA is 2.5 kilonewton. This is 7.5 kilonewton VA. Now bending moment at P. He is asking now bending moment at P is equal to 7.5 kilonewton into 2 minus 2.5 into 3. So 15 minus 7.5. So you will get 7.5 kilonewton meter. Seventh question, 7.5 means C. So first we will find VA, then HA you take the help of ILD, then bending moment at P means stand here, look left. VA into 2, HA into 3. Like that. Next. Means this is how you should calculate when calculators are not permitted and time is only 1 minute. See, I am reading the question. As I am reading the question, I am drawing the diagram. In the same way, you should also approach in the exam. Then only you can save the time. Because I have to write and explain, I may take say 30 seconds extra time. That 30 seconds you must save. Neat calculation we don't have to write because you have already studied. You have listened to my classes. When I write L by 4H, immediately this is ILD for horizontal thrust, you should get it. If not got, supposing that. Then first read the 3 hinged arches, 2 hinged arches chapter, go through that thoroughly, then read the workbook solutions. Then you, because just now you have studied that, then whatever diagram I am drawing, you are able to connect. Now if I write entire story, ILD for horizontal thrust, etc., in the exam also will tend to write and it will waste your time. Next one, a 3 hinged semicircular arch of radius A, radius is A, subjected to uniformly distributed load of W kilonewtons or W per unit length whole span, W per meter. The horizontal thrust is given by. So vertical reaction is W into this total distance is to A. So W into A here, vertical reaction W into A. Now bending moment at C is equal to 0. So you will get this one plus WA into A minus H into A minus W into A into A by 2 must be 0. So WA square minus WA square by 2 minus H into A, 0. So H will get WA by 2. Half of that, WA by 2, are here of radius L. On the whole span L, okay. He has taken it as whole span. WL by 2 means W, we should get WA by 2. So C is the option. So whole span L means 2A. So WL by 2 means W, first option will become WA, W2A, WA by 2. So A and D are same. Ninth question solved in the class. So root 2P, B is the option. This is solved in the class. Next, 10th question. 3 hinged loaded semicircular arch. This is a semicircular arch. What is the shear force at the hinge C? Shear force at the hinge A, this is B, this is C. So at this point, if you drop a tangent, it's like this. So vertically, you have to see. This is 20 kilonewton. So this you will get 10 kilonewton. This is also 10. So stand here, look left. So 10. So if you look left, 10. Don't want to look right, also 10. So correct answer is 10. It's like this. Due to 20, stand here, look right. At C means you can see left or right. 10. Don't want, stand here, look left, 10 only. That's why shear force at C directly they have asked at the hinge. Exactly under the hinge shear force is indeterminate, but that means he wanted either LHS or RHS. Then 11th one, linear arch is the one which represents center line of the arch, variation of bending moment, thrust line, variation of shear force. See here, linear arch means that line, that is the axial thrust line. So where bending moment diagram it will show, but not the variation of bending moment. So it is a thrust line. 11th is C. Next, 12th, symmetrical two-hinged parabolic arch when subjected to uniformly distributed load on the entire horizontal span is subjected to, this I have given you, radial shear, only normal thrust alone. 12B, solved in class. Because it follows the shape of bending moment diagram, it is like a funicular polygon. because due to UDL the shape is parabola. So bending moment shear force is 0. Cross section is subjected to normal thrust. This becomes like a theoretical arch. This is now the thrust line. Okay. Next. 12 is over. Next 13. Symmetrical parabolic arch of span 20 meters is hinged at springings. Symmetrical parabolic arch 20 meters hinged at springings. It supports a UDL of 2 tons per meter of the meter run of the span. So that means you have to assume full length. The horizontal thrust in tons at each of the springings. Symmetrical parabolic arch. That means again formula is same, WL square by 8H. So 20 meters. This is 20 meters. Rise is 5 meters. UDL is 2 tons per meter. So W is 2 tons per meter. Length is 20 square by 8 into H is 5. So 40. So 2 force 20 means 20 kilonewton. So 13th one 20 kilonewton. C. He is asking you the horizontal thrust that will develop. Next 14th one. 2-hinged parabolic arch. We have a 2-hinged parabolic arch. Okay. Vx is sum of vertical forces on the left hand side. Vx is the sum of vertical forces on the left hand side of the section. H is the horizontal thrust. Alpha is the angle of tangent at the point on the arch with the horizontal. The shearing force at the section from left hand side is given by, supposing that here it is given, this is sum of the forces. Vx is Vx, let us say upward. So here on the left hand side on this free body diagram, if I take it, okay, so Vx will act downward. Next, horizontal thrust is H. Theta also is given. Then sum of the shearing forces. Shearing forces means components like this you have to take it. This is also theta. So shear force, shear radial, H sin theta upward, section right side upward. He is asking on the left hand side. So whatever it is, shear radial, H sin theta minus Vx cos theta. H sin theta minus Vx cos theta. So only alpha he has given. So you write it as H sin alpha minus Vx cos alpha. So Vx cos alpha, H sin alpha. So on the left hand, now I am standing here looking right side. He is asking you stand here, look left side. So Vx here it is upward. This is right side. Okay. So reverse of that. This is stand at xx and look right. Stand at xx and look left, say. Then shear radial. So you will get plus Vx cos alpha minus H sin alpha. Other than this, no option is matching. So you don't have to worry whether which is plus or minus. So Vx cos alpha minus H sin alpha you can answer, or if they give this one, this is plus, this is minus, then also you can take it. Minus H sin alpha means this is B. 14th one is B. Like this you have to manage. Some of the forces he has given. So Vx upward, let us say. Then here Vx is downward. Horizontal thrust is H right side. So put left side here. So components you find. Shear radial means in this direction. Xx direction components. H sin alpha is this component. Vx cos alpha is this component. This angle is alpha. So 1 plus 1 minus you take it, enough. Now let us see the 15th question. A symmetrical parabolic arch of span hinged at both supports. We have like this. Arch carries uniformly distributed load W per unit length along the entire span, like this. Okay, is correctly matched. Horizontal thrust, correct, WL square by 8H. This is valid for 2 hinged and 3 hinged parabolic arch. Bending moment at crown, whether you take 3 hinged arch or 2 hinged arch, bending moment at C is 0 throughout. Bending moment is 0 everywhere. So second statement is wrong. Radial shear is 0 everywhere. So third statement is wrong. Vertical reaction, how much you will get? The span is W, this is L say. Vertical reaction how much? WL by 2. So vertical reaction is also wrong. So horizontal thrust WL square by 8H is only correct. Valid for 2 hinged arches as well as 3 hinged arches. That's why I didn't mention which arch it is. Because this result, when subjected to UDL, it is like a theoretical arch or linear arch. So whether central hinge is there at crown or not, result is same. Then 16. This I have told you already in the class. I0, I is equal to I0 into secant theta, or I0 into secant theta means square root of 1 plus tan square theta. I0 into square root of 1 plus tan theta means dy by dx whole square. Now you see I0 into 1 plus dy by dx whole square. So D is the option. Next 17. Symmetrical two hinged arch subjected to UDL on horizontal span. Two hinged arch subjected to UDL on horizontal span. If one of the supports settle down vertically, then the horizontal thrust is decreased. B. Decreased. Solved in the class. Why it is decreased, I gave you the reason. 18. Two hinged arch, an increase in temperature induces maximum bending moment at crown. This is also solved in class. A 3 hinged parabolic arch of span 20 meters arch of span 20 meters, central rise 4 meters. Central rise 4 meters. Carries UDL of 25 kilonewtons per meter. UDL of 25 kilonewtons per meter. This is a 3 hinged arch. UDL was there. If the arch is now subjected to a temperature rise of 40 degrees centigrade, then the change in horizontal thrust will be. So now initially horizontal thrust is H, WL square by 8H. W is 25 kilonewtons per meter. Length is 20 meters. WL square by 8 into H is 4 meters. Central rise is now 4 meters. So some value you will get. We will keep it as it is. Then subjected to temperature rise 40 degrees centigrade. Then delta H you have to calculate. Difference in the height L square plus 4H square by 4H into alpha into T. L square. This is the rise in the thrust. 40 square plus 4 into H square is 4 square by 4 into 4. This is the value you will get. Now decrease in the horizontal thrust. Change in horizontal thrust is minus dH by h, that's all, into capital H, minus dH, because it is decreasing. He is asking you only the change in the horizontal thrust. Simply dH he is asking, not the change. So minus dH. This is alpha is how much? You get 12 into 10 to the power of minus 6. Alpha into temperature change is 40 degrees centigrade. So this is the change in height. So dH by h. H is 4 meters. So into capital H you got it as this much. Now see, he has given the span, rise, load. Because of that, horizontal thrust is so much. Now, because of the temperature increase, the crown of the arch rises by dH amount, L square plus 4h square by 4h alpha into T. L square 20 square, 4h square by 4h alpha into T. You get 0.014 meters. So change in horizontal thrust is minus dH by h, dH by small h only, dH by h into capital H. Okay. So dH by h is 4 meters, capital H is this, 1.09 kilonewton you will get. It has given 1.0875, you can round it off to 1.09. So 19th A is the answer. So this formula I told you, not necessary to remember, but such questions L square plus 4h square, so many times we have done that, maybe you can remember. But like this, unlikely to be given in the exam. Next, 20th question we solved already. In a two-hinged arch, an increase in temperature induces no bending, uniform bending, maximum bending at the crown. Okay, explained in the class. Next, 21.